Hello and greetings from Calgary. My name is Russell Shanahan and I'm a PhD candidate at the University of Calgary, supervised by Dr. Yaron Still. Today I'll be presenting some of the polarization results from the Thor survey and give you our interpretations and the implications our results have on galactic magnetism. The H1OH recombination line, or Thor survey, observes the inner galaxy from longitudes 14.5 to 67.4 degrees with a latitude range of plus or minus 1.25 degrees. The Thor continuum observations range from 1 to 2 gigahertz in Stokes I, Q, and U, with channels of 2 megahertz and an angular resolution of 20 arcseconds on the low frequency side to 10 arcseconds on the high frequency side. The survey also includes atomic hydrogen spectral line, 4 OH spectral lines, and 19 hydrogen radio recombination lines. The results presented in this talk were derived from the continuum observations. So for more information on the survey and other works, please visit the website or check out the first data release paper. We use two methods to investigate polarization and Faraday rotation from Thor. These methods are Stokes Q fitting as shown above, as well as RM synthesis and RM clean shown in the below panel. Some key metrics for RM synthesis using Thor data includes the Thor Faraday depth resolution of 100 radians per square meter, as well as the maximum observable Faraday depth with no channel averaging being 26,000 radians per square meter. With channel averaging, the maximum observable Faraday depth is reduced to 6,500 radians per square meter, and the largest Faraday depth scale is 150 radians per square meter. Here I present the rotation measures for extragalactic radio sources observed from Thor. The full data set will be published in an upcoming paper, Still et al., and the green and cyan curves are rotation measure predictions through the plane of our galaxy from previous publications. So what we observe is a spike in rotation measure up to 4,219 radians per square meter, observed on the inside of the Sagittarius arm tangent, with several sources exceeding 2,000 radians per square meter. On the low longitude side of the spike, where the line of sight intersects the Sagittarius arm, the mean rotation measure is 54% higher, with a standard deviation 63% larger than what is observed on the high longitude side, where the line of sight does not intersect the Sagittarius arm. So from this, we hypothesize this is caused by a compressed warm ionized medium upstream from the major star-forming regions within the arm. The bottom plot is a zoomed-in version from a previous publication where we show the rotation measures observed from various supernova events just on the inside of the tangent. And what we see is that the supernova rotation measures fall on the lower side of the extragalactic source rotation measure spread, which indicates a positive Faraday depth from regions within our galaxy beyond these supernova events. So we propose that from this data, there's a counterclockwise magnetic field inside the Sagittarius arm, and that outside the Sagittarian arm, there's a region where the magnetic field is also counterclockwise. So from this, the higher rotation measures observed from Thor demonstrates that future rotation measure predictions for the Milky Way need to account for the excess Faraday rotation from compressed warm ionized medium on the inner side of the Sagittarius arm. The figure on the left is from Hanatal, where they compared pulsar rotation measures with their distances and dispersion measures in conjunction with previously published extragalactic radio sources to argue a magnetic field reversal in the outer part of the galaxy. The figure on the right shows pulsar rotation measures versus their dispersion measures from the same longitude range as seen on the right, but with the latitude range restricted to what is observed with Thor. The yellow histogram shows the distribution of the pulsar rotation measures, and the purple histogram is a rotation measure distribution for extragalactic radio sources from Thor, with the black dashed line indicating the median rotation measure. So what we find is that the extragalactic rotation measures from Thor increase the amount of Faraday rotation observed through the galaxy. And we propose that this result implies that we do not find a reason for the kind of reversal proposed in Han et al. However, if rotation measures observed for the higher dispersion measured pulsars, this interpretation may change. I'll now switch gears and present the polarization results from supernova remnants on the low longitude side of the Sagittarius arm tangent. In an upcoming paper, I will present the results of all four that are highlighted here. But for the purpose of this talk, I will only discuss the two seen in green. I'll first show G46.8, where on the left-hand side is the Stokes eye image of the supernova remnant, where the red box is the area where we performed a blind search for polarization and Faraday rotation, which was broken up into subregions the size of our beam. The figure on the right shows the Faraday depth map of the supernova remnant, where each colored pixel is for a subregion where we detect polarization and Faraday rotation. The pixels with the purple border indicate where two-component Faraday rotation is observed. Blank pixels or white pixels are, of course, non-detections. Here I show a Faraday depth grid plot for the subregions within the red box indicated on the left, where the black spectra are for subregions that do not pass our detection criteria. The blue spectra indicate a single detection, and the purple spectra indicate subregions where two-component Faraday rotation is observed. The vertical gray region and the horizontal red line indicate our detection criteria, but we also reject peaks that are below 1%. So an accepted peak has to be outside of that gray region, above the red line, and has to be higher than 1% fractional polarization. Here I present the fractional polarization map of the supernova remnant, where the black pixels correspond to regions where we detect no polarization, but we derive an upper limit for polarization to be less than 1%. Since these subregions correspond where the supernova remnant is the brightest, we propose that the lack of polarization indicates depolarization due to a turbulent magnetic field within the supernova remnant itself. Here we show the Faraday depth map for the supernova remnant G39.2, where as before, the colored pixels correspond to regions where we detect polarization as well as Faraday rotation, and the purple bordered subregions indicate where we detect two-component Faraday rotation. And from this, we see a lovely gradient from the bottom part of the shell up towards the top. Now, zooming in on one of these grid plots, we can see small-scale structure in both Faraday depth as well as fractional polarization. Now, note the gradient from the left to the right, as well as the abrupt increase in Faraday depth at the bottom. Now, in this figure, we are able to see the real power of Thor in being able to detect small-scale structure in not only polarization, but also in Faraday depth. To highlight this spectrum, where we see two-component Faraday rotation as a demonstration of one type of complex Faraday rotation that we observe. The second type of complex Faraday rotation is seen in this subregion, where we have a strong single component that depolarizes across our frequency band. So we propose that we're observing structure within the supernova remnant itself, as opposed to structure along the line of sight in the interstellar medium. As a little bit of a cartoon, so since we don't observe synchrotron emission that's obscuring the supernova remnant, along the line of sight, multi-component Faraday rotation cannot be a result of the effects from the interstellar medium and must be internal to the supernova remnant itself. Whereas a single component Faraday rotation that's depolarized could originate from the far side of the supernova remnant shell as it becomes depolarized either through a turbulent magnetic field within the supernova remnant or from the near side of the supernova remnant shell. So from the polarization map, we see again upper limits below 1%, the black pixels, corresponding to regions of strong Stokes eye emission, indicating that there's enhanced turbulent magnetic field. We also see Faraday rotation from the galactic diffuse emission that predominantly shows up on the edges of these ionized regions because of a sharp gradient in rotation measure along with spatial filtering of the VLA and C array. From the Faraday depth distribution, we see a narrow as well as a broad peak. So we propose that the narrow peak corresponds with the front side of the supernova remnant shell, where the spread is caused by the Faraday dispersion from the interstellar medium on scales of our beam. And the backside of the supernova remnant corresponds to the broad peak, where the dispersion is caused from internal structure in the supernova remnant, as well as the nearest part or the near side of the supernova remnant shell. So we propose that this type of structure is not unique to just one supernova remnant. So we say that the Faraday depth distribution for G46.8 also has a similar shape, but from a different angle of the large-scale magnetic field, we see a broad and a narrow peak to have the same or a similar Faraday depth. The key points from this talk are that from extragalactic sources, we see an enhanced line of sight magnetic field or an excess of free electrons on the inside of the Sagittarius arm caused by a compressed warm ionized medium. We also propose that there's a reduced need for magnetic field reversals because of these higher extragalactic rotation measures that we've seen from Thor. From supernova remnants, the lack of polarized emission from bright regions shows evidence of an enhanced turbulent magnetic field. We also propose that we find evidence for internal Faraday rotation within the supernova remnants G46.8 as well as supernova G39.2. Thank you very much for having me. Cheers.